Hello, everyone. So this lecture is going to concern chapter 2 of the textbook. We're going to talk about definition of velocity and acceleration. The goal of the second chapter is to study one-dimensional motion. So let me go ahead and I'm actually going to share my screen and we'll take a look at the chapter real quick. So let me share that. So again, to get to the textbook, we can go over here in the Canvas shell to Wiley Course Resources and click on that. And it should bring up all of the resources you have here. And we'll hit launch for the e-textbook. So let's just take a quick look at chapter 2 as soon as it loads. And so chapter 2, again, is motion along a straight line. And one of the reasons we're going to study motion to begin with is it's simple, right? And in fact, in general, motion is going to be along 2 or even 3 dimensions. But starting with 1 dimension makes it a little easier to deal with, and then we can easily extend it to 2 or 3 dimensions. So looking at the first part of chapter 2, we're going to talk about position, displacement, and average velocity. And that's basically what this lecture is going to be about. I'm just going to talk about that. So let me go ahead and begin that discussion by talking about, in general, about maybe some of the stuff that you hopefully read about in chapter 1. Chapter 1 was about just units. And so I'm kind of assuming that everyone's pretty familiar with units and converting units. And the first homework problem set in that module is about that sort of stuff. So again, if you have questions about that, let me know. But one of the things that you probably saw there was that, let me share my screen here. One of the things that you hopefully saw there was that we have this metric system of units that we're going to typically use, or it's often called the SI system, international system of units. But in the SI system, the fundamental units that we are going to deal with this term have to do with some quantities, right? And so we have the quantities. And what are quantities? Well, they are things that can be measured, because in science, we are going to make measurements, and we are going to measure certain quantities like the length of something or the speed of something that we're going to talk about in this chapter. When we make those measurements of those quantities, we all need to agree on what amount we're getting, and that brings us to our units. So all of this is covered in chapter 1, but the main thing I wanted to point out is that we have some fundamental units. And they have to do with length, also mass, which we won't get to for a little bit, and time. So the length unit in the metric system or the SI system is the meter. The mass is the kilogram. Kind of interesting that it's the kilogram and not the gram. And time is the second. Okay, now, so these are fundamental quantities. As we are going to see, we're going to develop other quantities that we can measure that are going to be combinations of these units. One example of that would be the density. And density is mass over volume. Right? So to get a density, you'd actually have to measure the mass of something and the volume that it was occupying. But its units are going to be kilograms per meter cubed. And as you can see, this is a combination of those fundamental units. And so this is typically what's going to happen. We're going to have combinations of units. Now, there are a couple of different types of quantities I wanted to point out. So types of quantities. In fact, there are 2 of them that we are going to deal with. And those 2 types are scalars and vectors, right? Or scalar and vector quantities. Now, scalar quantities have only a magnitude. Now, what do I mean by a magnitude? I mean a number, right? An amount. So as an example, mass is a scalar quantity, right? It has only an amount. I might say 5 kilograms. I don't say 5 kilograms to the west. And that's what distinguishes a vector. Vectors have a magnitude and a direction. And an example of that would be a thing we're going to talk about in this lecture, velocity. Now, you probably have a feeling or you've dealt with velocity, maybe in your calculus class. But velocity has both a magnitude and a direction, right? You say, I'm going to travel in my car at 20 miles per hour to the east. That would be my velocity. Now, as it happens, sometimes we like to say we're just, oh, I was going 20 miles per hour. And that would be your speed. So velocity is your speed plus your direction. And so, in fact, I would say speed is really a scalar quantity because I just say 20 miles per hour. It's just a quantity that doesn't have a direction. Velocity would be the vector quantity. Another quantity we're going to talk about in this chapter that is a vector is acceleration. And another one that even is kind of more fundamental than velocity acceleration is displacement. Okay, so I just wanted to talk about those types of quantities. So let's go ahead and now define what I mean by displacement and velocity. Okay. So first of all, if I'm going to describe the motion of something, the first thing I really need to do is describe where it is. And I'm going to call that its position. The position is telling me where it is. Now I have to, in assigning the position, I need to give it or tell me, have an origin, right? I need to know where I'm measuring its position from. So I might say, okay, it's 5 meters from the wall. So the position, I'm going to denote by the letter X. So that's my variable. Now, sometimes as we'll see later, we might talk about a ball going up in the air. We might define our position to be Y in that case, right? But it's just a variable defining maybe how far it is from the floor, but I've always got to have that reference point, that origin. Now, once you consider motion, you're going to be moving around. And so you're going to have a final position, which I'm going to call XF with a subscript, and an initial position, which I'm going to call X sub I. All right, so we're going to move from an initial position to a final. So for example, if I'm just moving along a straight line, maybe I've got X equals 0 here, and I'm going over to the right in my negative or in my positive direction. To the left, I might be going in my negative, right? So my X equals 0 point, my origin is right there. So let's say I moved from X initial equal to 2 to X final equals -1. Right? I would be moving backwards, right? I'm moving to the left. This is my initial position, and I'm moving over here to my final. Now, I'm going to define something called displacement. And displacement basically is just the distance that you have moved from where you started to where you finished. So it's just going to be X final minus X initial. Now, since it's a change in X, I can use the mathematical notation delta X. So sometimes, and in the book, you will see the displacement called delta X. And one thing I do want to point out is that displacement is a vector quantity, right? When you're dealing with just one-dimensional motion, you only really have two directions. You have either right or left, or positive or negative. So in our example, the displacement is actually negative, right? Delta X is -1 minus 3, and we're going to call these meters. So it's -4 meters. And the point is that the negative sign there is telling me the direction of that displacement. You move 4 meters to the left, or 4 meters in the negative direction. Okay. So that's the definition of displacement. Position and displacement will get a little trickier when we go to 2 dimensions, because now you're going to have not just an x coordinate, but a y coordinate as well. But we're going to get to that in the next chapter here. So let's just stick with our one-dimensional motion. And our next quantity that we want to define is our other vector quantity, velocity. Okay. So when I talk about velocity, I mean how far I moved divided by the time it took me, right? It's going to be in meters per second in the metric system. So it's going to be related to displacement. It's going to be displacement over time. And in our notation, I could use delta x over delta t. Right? So let's just say that in our example, it took us maybe 2 seconds to make that -4 meter displacement. So our velocity, we'll call it v, right? So v will be our variable for velocity, is going to be our delta x over delta t. So it's -4 meters over 2 seconds. So it's -2 meters per second. Okay, so I was moving at a rate of -2 meters every second to the left. Again, the negative sign is telling me the direction. Another important point to realize here is that this is what I would call an average velocity. So this is an average velocity. What do I mean by that? Well, there are multiple ways that I could go from this point to this point. I could go at what I would call a constant velocity, so that I just stayed at a speed of -2 the entire time that I was moving. But on the other hand, I could have also gone a little more quickly at the beginning and slower at the end, right? Now, typically what you would do is you would start out at 0 velocity, speed up, and then slow back down maybe as you come to a stop or something. That would be another example of moving between those 2 points. As you can see, my velocity is not going to be constant if I do that. But my average, my calculation using this definition is still going to be -2 meters per second, because all it does is take the distance or displacement I covered and divide by the time. It doesn't concern itself with how I actually moved in whatever way I did during the time I was moving. So this is an average velocity. It's not what I would call an instantaneous velocity. An instantaneous velocity would be your velocity at a finite moment, right? An infinitesimal moment in time. Maybe it's a good exercise to make a graph of this. Let's graph our velocity versus our time. All right, so here's a graph of velocity versus time. So let's put on some coordinates here. So 1 second, 2, 3, 4, 5. So this will be in seconds, and our velocity will be in meters per second. And maybe I won't put some numbers. I just want to kind of show the graph here. So let's say I moved at a time of 1 second. Well, yeah, actually, we'll also make a graph of our display of our position versus time. I think that would be good to compare, right? So let's graph x of t and v of t. And then we'll correlate how the x of t graph correlates with the velocity. Oh, should be seconds again. 2, 3, 4, 5. And then we could go to our negative values of position. But the main thing I want to point out is, let's say I am going to move from this point maybe to this point. So we're going to go now from x equals 1 to 4. And I'm going to do that over a 2-second period, right? So I'm going to start here, and I'm going to go, or let's say after 3 seconds, I'm going to go to right there. Again, there are many different ways that I could go from that point between those 2 points. I could go at a constant speed. Now, if I'm going at a constant speed, what's going to happen is I am just going to make an exactly, whoops, going to miss that. It's going to be a straight line because I'm covering the same distance for every second, right? And so if I got the slope of this line, right, delta x over delta t, that is my velocity. The problem is that the only time the average velocity is going to equal the velocity, instantaneous velocity, is if it is a constant velocity like this. Again, I could make many different motions. I could maybe start out fast. Now, if I started out fast, I would have a bigger slope. Then maybe I start to slow down and eventually I hit a flat line, right? A slope of 0. So I have actually reached 0, and now I'm going to turn around and maybe go backwards a bit. Now I've got a negative slope at this point. I have a negative velocity. I'm actually going the other direction, right? And then I turn around, speed back up until I hit the point. So you can see there are an infinite number of ways I could go between those 2 points. My average velocity is just the average over the whole time. Now let's look at what if I had, I was moving from this point to this point at a constant speed. What would the graph look like? Well, the slope is the velocity, and it would be a constant slope. So I would just get a flat line, right? I would have a constant slope. My velocity is the slope of the position graph. Now, for this one, you might try to figure out what it looks like. Okay, well, in the first part of the second part of the graph, I've got kind of a higher velocity. So maybe I'm starting up here. Now I slow down to 0. I'm not going to try to correlate it. So I'm down at 0 now. And now in this part, I've gone to a negative velocity, but I'm turning back to 0 at this point where the slope is, right, it's a flat line, its slope is 0. So I'm going to come back through 0, and then eventually I'm going to get very fast, right, really quick. I'm going to go up to a high velocity when I get finally back to my point there. So the point of this is that I want to make sure you understand the difference between average velocity and instantaneous velocity. The instantaneous velocity is the slope at any particular point in time, right? So I've got a high speed here. Here, the slope of the tangent line is 0. So when I turn over, my instantaneous velocity is 0. Then it becomes negative as the slope starts to go down. Okay, so you've probably seen some of this in your calculus class. The next thing we are going to do is we're going to talk about acceleration, and we're going to actually do some calculus because, of course, probably remember from calculus that if I want the instantaneous velocity, right, the slope is actually the derivative of my position graph. It's dx dt. So we're going to do some examples with that in the next lecture.